Okay, another example, we have a spherical shell. And there are a couple of holes in the shell so that a mass released out here can fall right through this shell. Just a small hole where this very small mass can pass through. These objects are gravitationally attracted. You got gravitational force of magnitude G big M little m over r squared when they're separated by distance r. So you release from some point r equals r naught. What's going to happen? This thing is going to pass through here, picking up speed at least till it reaches the boundary of the shell. Now, we haven't talked about it yet, and it really involves multivariable calculus if you want to prove it. But inside the shell, there's zero gravitational force between these things, assuming this is a symmetric shell. So that it picks up speed till it gets to this point, then it coasts along till it gets to this point, and then it goes on losing speed now that it's being pulled back toward the object until it gets out to a point on the opposite side, same distance on the opposite side, easy to prove that, and then it falls back. Now, we're assuming there are no dissipative forces. So this thing's just going to keep going back and forth. Okay, is that harmonic motion? Well, yes, that is harmonic motion. Okay, it's moving with the same period between the same points. And that's harmonic motion. It's that simple harmonic motion so that we can model it as we modeled pendulums and masses on springs and so forth. Well, that's the question. So you have to ask yourself, okay, well, what's the condition for simple harmonic motion? That's the first thing I told you about simple harmonic motion, if you're in my class, and nobody can tell me, because you don't pay any attention when I say, you got to remember this. Well, that's because you're sorting it out and you get to lose the forest for the trees, and I'm trying to bring you back to the forest. Simple harmonic motion occurs under what conditions? It occurs when you have a linear restoring force. Not only linear, but a restoring force proportional to your distance from some equilibrium point. Now, do you have a linear restoring force here? Well, your restoring force, the force that pulls you back toward the equilibrium position, at least if you start from outside, is an inverse square force. That's not like a negative kx force. This is not simple harmonic motion. It's harmonic because you go from this point to equal distance on the other side and back forever if there are no dissipative forces. But simple harmonic motion requires that your net force is negative kx. Here, your gravitational force would be your net force, and it's not of the form negative kx or negative, it could be negative kr, it doesn't matter what letter you use for this, but it's not. Okay, so your net force is not of this force, it's not of this type. If it was simple harmonic motion along the r-axis, of course, you'd have f net equals negative kr, as I think I just said, and you'd have r of t equals a cosine omega t plus phi, because that follows immediately. Is it so? No, it's not so. Here's your force. This isn't your force, this is your force. Completely different nature. You're off by 3 powers of r. Okay? A positive first power or a negative second power. You're off by 3 powers of r. It's not even close to being simple harmonic motion. It's harmonic, not simple harmonic motion. So I say, okay, here, but the net force is this. The form is net force is negative k over r squared, where k would be your g big M little m over, well, just your, yeah, g little m big M, that would be your k. Okay. Now, there's more to this, and I haven't even thought through what I'm going to say next. I'll just say that, okay, we were able to solve this, okay? In this case, you had mx double prime equals negative kx, and that it was easy to at least verify that your general solution is of the form either a, or so let's say b cosine of omega t plus c sine of omega t with possibly a phase angle in there, or equivalently of this form. And we've been through this in detail well over a month ago. So this is simple harmonic motion. You should recognize all of this. You should be able to reproduce this at any time. This equation is not one that you want to deal with, okay? It's a much tougher equation to solve. There's no obvious solution. You have to use all kinds of methods that you don't know anything about now and are beyond the scope of this course. So I said that's too advanced for us at this point to solve. Now, if you take differential equations next semester, as most of our students will be doing, then yeah, you can solve it. But even there, it's one of the more difficult things to do in that course. So that course isn't a prerequisite or even a co-requisite for this one, so it's clearly we can't expect to try to solve it. This solution just results from knowing first semester calculus and a little bit of circular trigonometry, which you should know from pre-calculus. Okay, so we can't solve this, but we can say things about energy. The potential energy of this system, I said, is big G, big M, little m over r. And depends on where you do potential energy relative to, but usually we're going to do it relative to infinity, so it'd be negative. But anyhow, there's your total energy of the system. And your kinetic energy is just a difference in the potential energies between 2 points. So there's lots that you can do with energy, but let's not belabor that. Okay. Now, turns out, you got a differential equation here that we know how to solve just by knowing about the derivatives of the sine and or cosine function and how we could combine a sine and a cosine function into a single sine or cosine function. Here we can't solve it, but it's an interesting differential equation. Okay, in this course we have 5 basic differential equations. One is mx double prime equals f net. We're familiar with that. That's just mass times acceleration equals net force. Mx double prime equals negative kx that we just talked about. That's for simple harmonic motion. And it's just an instance of this, where your f net is your negative kx. We have I theta double prime equals negative k theta. Okay, well that's just for rotational motion. Instead of mass, you have moment of inertia. Instead of position x, you have angular position theta. So this equation is just the same as this equation, except in a different context, with slightly different values of your constants. You have mx double prime equals negative kx plus the force of friction. Well, if you have a constant force of friction, it turns out that this is a very easy equation to solve. You can solve this just with knowledge of first semester calculus, if you see how the solution comes about. We might or might not talk about that one. And then we have I theta double prime equals tau net. Okay, and that's very much like this equation. But tau net could be a more complex function. We might or might not be able to solve this equation.